All right, today we're digging into RISC Zero, a technology that's really changing how we think about trust online. Look, we live in a world that's just run by software, right? But how do you really know that code is doing what it's supposed to do, especially when it's running on some server somewhere in the cloud that you'll never see? And that's the big question, isn't it? Whether it's a cloud server crunching your data, or a smart contract moving millions of dollars, or even an AI making a decision, you're basically just taking its word for it. You're hoping it's doing the right thing. But what if you didn't have to just hope? Well, the answer is, in theory, pretty simple, but it is incredibly powerful. What if the computer could just hand you a receipt? Not a paper one, but a cryptographic receipt that is mathematically impossible to fake. A receipt that proves, beyond any doubt, exactly what program it ran and exactly what result it produced. This isn't some far-off sci-fi idea. It's here now, and it's the heart of a whole new way of computing. So this idea of a cryptographic receipt is the key to something called verifiable computing. And it is a fundamental shift in how we approach trust in the digital world. And here's why this is such a game changer. You no longer have to trust the machine doing the work. And this is the important part, you don't have to rerun the massive computation yourself to double check it. All you have to do is check the proof, which is tiny and super fast to verify. It basically separates the question of how the answer was found from the simple fact that the answer is correct. So this is where RISC Zero enters the picture. They've built the system that makes all of this a reality. And the really cool part is that they've made it accessible. Developers can write code in normal everyday languages like Rust and C++, and the system automatically generates these proofs for them. This is a huge, huge deal for bringing this tech to the masses. Okay, so how on earth does this actually work? Let's pop the hood for a minute and take a look inside their zero-knowledge virtual machine, or zkVM, to understand the really clever decisions that make it all tick. You know, one of the most critical decisions they made was what to build on. Instead of choosing something complex and specific like the Ethereum Virtual Machine, they went with RISC-V. Now, you can think of RISC-V as a very simple, clean, open-source language for a processor. And that simplicity? It's everything. Because it is so much more efficient to create mathematical proofs for simple, predictable instructions than for complex ones. So here's how it all comes together. First, you take your normal code and combine it into that simple RISC-V format. Then, you run that program inside their special zkVM. As it runs, the machine keeps a detailed log of every single step. That's called the execution trace. That trace then acts as the raw material to generate a Stark-based proof. And finally, that proof is bundled up with the public results of the program into that neat little package we call the computational receipt. Now, as you can probably guess, generating these proofs takes a ton of computing power. The story of RISC Zero, especially in 2025, has been this incredible, dramatic race for performance. But it's also been a story about facing some pretty serious security wake-up calls along the way. I mean, just look at these numbers. To generate a proof for a single Ethereum block, their first version took about 35 minutes. With version 2.0, it dropped to 44 seconds. And their goal for the end of 2025 is to get that under 12 seconds. The pace of improvement here is just staggering. Yeah, this chart really puts it into perspective, doesn't it? That drop from version 1 to version 2 is not just an improvement, it's like a whole new category of performance. A big reason for this massive speed up was the introduction of precompiles. You can think of these as highly optimized special-purpose circuits for really common and expensive calculations, like hashing. So why is 12 seconds the magic number? Well, that's the block time on Ethereum. If you can generate a validity proof for a block in under 12 seconds, you can prove every single block in real time as it's being created. That's pretty much the holy grail for a verifiable blockchain. But with all this power comes some pretty big risks. In early 2025, a critical security flaw was discovered. A single missing mathematical check in their system meant that a malicious user could generate a proof that looked perfectly valid for something that was mathematically impossible, like proving that 7 divided by 5 has a remainder of 0, which, it doesn't. A bug like that completely breaks the trust the system is supposed to create. But here's the thing. It's not about never having bugs. It's about how you respond. And this timeline shows a clear path toward real trust. After a big audit, they started using a technique called formal verification, which is basically using math to prove your own code is correct. So when that vulnerability was found in May, they patched it quickly and doubled down on this approach. It shows a real shift from a model of trust us, we wrote good code, to don't trust us, trust the math. And that's the whole point, right? So once they had this incredibly fast and increasingly secure proving machine, what was the next step? Well, you build an entire economy around it. And that led to the creation of the Boundless network. This was a pivotal moment. RISC Zero basically fired itself. They shut down their own centralized service for creating proofs and instead launched Boundless, a completely decentralized and open marketplace. Now, anyone who needs a proof can put out a request, and anyone in the world with a powerful computer can compete to generate it and earn a reward. They turned computational correctness into an open commodity. The whole network runs on the ZKC token, and if you look at how the tokens are distributed, it tells you a lot about their strategy. Almost half of the entire supply is dedicated to ecosystem and strategic growth funds. That's a huge signal that their number one priority is bootstrapping a healthy, vibrant community of both developers and provers. And the incentives here are really powerful. The provers, the people doing the heavy lifting, get 75% of all the network rewards. To kickstart things, the early rewards for staking and securing the network were massive. But there is a stick to go with that carrot. If you're a prover and you fail to deliver a correct proof on time, half of your staked tokens get burned. Poof, gone. This makes sure that everyone has real skin in the game. So where are things heading? Well, the next major leap for RISC Zero, and really for the whole field, involves going all the way back to the absolute basics of how computers work, zeros and ones. Here's the core idea. Most zero-knowledge systems today operate using math based on large numbers called prime fields. But this next-gen protocol, called Binius, works directly in binary fields, literally just zeros and ones. It's designed to speak the native language of a computer chip. The result is that a simple one-bit operation is about 13 times faster than a standard one. It's a fundamental redesign for pure speed. And it's not just about software. The hardware is evolving to match. We're now starting to see specialized hardware called verifiable processing units, or VPUs. These are chips designed to do one thing and one thing only, generate proofs as fast as possible. Look at this. A dedicated VPU is over 5 times faster than a top-of-the-line NVIDIA 4090 for a key part of the process. This is the future, software and hardware designed together. Of course, RISC Zero isn't alone in this race. The whole zkVM space is heating up. You got competitors like SP1, which is very focused on using precompiles for blockchain tasks, and Jolt, which is pushing some really cutting-edge theoretical approaches. RISC Zero seems to be carving out its niche as a universal, general-purpose machine that's also relatively light on memory usage, which makes it accessible to more people. And that really brings us to the final big question. What happens to our digital world when correctness is no longer about trusting a big corporate brand, or a server administrator, or a developer's reputation? What happens when it becomes a simple commodity, something anyone can verify with math? What new applications, what new kind of internet can we build when truth is no longer a matter of faith, but a matter of fact?